Yes, class. So a portion of earth magnetism was left from this lesson. Let us quickly complete this so that we can start with electromagnetic induction. Now, before we start with earth magnetism, what is the formula? What is the ratio of magnetic field? You have to understand certain terms in this. When we are talking about certain terms, you have to understand those terms because there are two different magnets here. One is earth acting as a magnet, right? So it will have its own axis. And one is the natural axis of earth, right? The natural axis of earth on which the earth rotates. So you have to differentiate between these. Clear? You have to differentiate between all these things. So when we say earth magnetism, we basically manifest the fact that this is north pole, this is south pole. Like this, we can replace the entire earth by just a single magnet. This is what we mean when we use the term earth magnetism. All right. So few basic terms you have to understand when we are talking about earth magnetism. See, this is the north pole, this is the south pole. This I have taken. This is the magnetic north pole class. This is the magnetic south. When we are talking about the magnets, north and south. So it's like earth is behaving like a magnet, bar magnet, you can say, for reference. So what all things will be there? We have studied about the axis. One is the geographical axis of earth. Suppose the earth rotates on this axis. So I'll say this is what? This is the geographical. This is geographical axis of rotation. The axis on which the earth rotates. Fine. Now, this is the axis of earth. Apart from this, there would be an axis along the bar magnet. That is the magnetic axis. That is the magnetic axis. So there are two different axes. That's why I'm saying understand the terms separately. You will be able to relate them. So this is basically when we use the term here, this is magnetic axis. This is the term magnetic axis. Clear class? This is the term magnetic axis. So here you are having two different axes. One. Secondly, we have to understand North Pole and South Pole. When I say, suppose this, I'm referring this to as North. So this has to be, is it Earth's magnetic North Pole? Is it? Or is it actual South or North Pole? This you have to remember. Fine. So when I use the term here, I'm actually referring to the term when I'm talking about this magnet. This is magnetic North Pole. Magnetic North Pole. Similarly, when I'm talking about this, this is the magnetic South Pole. This is magnetic South Pole. Now there is one equator of the Earth. There is one equator of Earth. That is a line which is dividing the Earth into two parts. This is known as the geographical equator. Equator of Earth. Now, when we were studying the terms in last class, when we were studying about the terms, that time I had discussed with you all these terms: magnetic axis, meaning of magnetic, this magnetic equator. So that time I told you the line which is intersecting the magnetic axis is known as magnetic equator. So here also you will have the term. This term is magnetic equator. These terms you have to remember. That's it. All these terms you have to remember. Now class, there are few lines which you have to remember. Meridians are also present. I'm not writing the meridians over here because see, this is already crowded and it will be messy if I'll tell you the meridian. So see, I'll tell you the meridians separately. But before that, you have to understand what is the geographical axis. Straight line passing through the north and south pole. The actual axis on which the earth rotates, about which we have been studying from our lower classes. Then you have magnetic axis, you have magnetic equator. I'm not writing their definitions again because you already know them. What is meant by geographical meridian? Geographical meridian, whenever we talk about geographical meridian, it's actually, see, one is meridian of Earth. When we, that is the geographical meridian. Suppose Earth is present, there's a line which is passing. So that real actual meridian of Earth, we call it as the geographical meridian. Then we have a term which is known as magnetic meridian. There's a term which is known as the magnetic meridian. So magnetic meridian is Earth's magnetic field acts in the direction of magnetic field. I'll tell you this, all these meridian things, this will be clear. Wait. Suppose this is the magnetic meridian. Magnetic meridian is basically line that is passing through the magnet. It is like the length of the magnet. Magnetic meridian, line through which the field lines, magnetic field lines are crossing the Earth. So this is magnetic. This is magnetic meridian. Fine. Then you have geographical meridian. Then you have a term which is known as geographical meridian. Let's say this is at some angle. This term is known as the geographical meridian. So this is what I was saying. This is known as the geographical meridian. This is geographical meridian. All right. Line which is passing through the Earth. This is through the magnet. Now there are angles which you have to remember. Before we talk about angles, let's say there is Earth's magnetic field in a certain direction. Now just understand some angles. There is an angle between geographical meridian and the magnetic meridian. Geographical meridian and magnetic meridian. This angle that is being subtended, this angle. This is known as angle of declination. This we represent through alpha. This is known as angle of declination. Then there is one angle. This is magnetic field B. Fine, this is magnetic field B. This is the magnetic meridian. So the angle between magnetic meridian and magnetic field. Magnetic meridian is present and magnetic field. This angle is known as angle of dip. This angle we represent it through delta. This is known as angle of dip. This is known as angle of dip. Now we have magnetic field in an absurd direction. Can you see the magnetic field is just in a random direction? It's not even touching magnetic meridian or geographical meridian. This is not perpendicular. This is not making a certain angle. So we have to resolve the vector. We'll resolve this one angle and there is one angle. So the axis with which the angle is made, that axis is called as cos. We use the term component cos. So this horizontal one is called B cos delta. This vertical one, this is called B sine delta. Fine. Angle of dip is what? Angle of dip is the angle between that the magnetic field makes with the magnetic meridian. Fine. If you want, I will write down the definition. Nextly, when we talk about the calculations, you just in the calculation part, just remember horizontal is B cos delta, vertical is B sine delta. When we take their ratio BV by BH, this is equal to B sine delta by B cos delta. BB will be cancelled. Can you see BV divided by BH is equal to tan delta. This is one information to be used. BV by BH is equal to tan delta. And see, both are at an angle of 90 degree to each other, horizontal component and the vertical component. So net magnetic field will be equal to under root BH square plus BV square. BH square plus BV square. Simple parallelogram. One thing I'll add more is that when we are talking about magnetic equator, see, at the equator, this delta value, because see, if this is the angle, see, this is the angle, at the equator, this will be like this. This is the equator, magnetic field at the equator. So angle is 0 degree. So when we say B horizontal, this becomes B cos 0 degree, which is equal to B. Can you see this is the maximum value B that can be achieved. Fine. Next, if you have magnetic poles, if we have magnetic poles, then this one, this angle will be, see, at the equator, this was this, at the poles are at the bottommost or topmost part of the, so at the equator it was like this, at the poles, angle 90 degree. So the angle that is formed over here is 90 degree. This is 90 degree. So BH is equal to B cos 90 degree, which is equal to 0. So the minimum value that is possible. All right. So that is all about earth magnetism. This is the core concept regarding formula. Theory part does not come much from earth magnetism. So that is not very important for you. Just go through it once. Everything that is written in the class, this part is important. All right. Write down. These terms are also not asked. I have not seen these are asked in the exams. But you have, anyways, I just tell you things which are important or unimportant from revision perspective so that it becomes easier for you. Write it down. This completes chapter 5. We'll start with EMI. But first write it down, get your doubts clarified. And class, I have been repeating this. If you all want any doubt class to be arranged, please let me know. One doubt class can also be arranged. Fadil, Sidra, Rajita, Mir Hussain, Amna, Alisa. Yes, class. Can we start with EMI now? So the first topic is magnetic flux. But before we start with magnetic flux, see, this is unit 4, which has EMI and AC. Both the lessons are small. EMI is a very small lesson. By the next week, we'll be able to complete it. All right, next week, we'll be able to start AC also. This is a very small lesson. It's easy. And class, it is very easy to score and it is interesting also. This lesson, it's not difficult and easy topics are there. The chapter is divided into small topics, so you have the portions from there. Chapter 6 is this, chapter 7 is alternating current. Then only one will be left, that is EM waves, which is the smallest lesson of all. So all those who were worried about the syllabus initially, be relaxed now. The syllabus is fine. You all are already studying second book in the next batch. See, the concept of electromagnetic induction is basically electro means electric field. Magnetic term only tells you that this is about magnetism, and induction means to induce something, to induce charge. The way when we were studying electrostatics, that time we initially studied about the term induction, right? Charging by induction, charging by friction and all. Now, initially, there was a concept which, see, the way the chapters are listed in NCERT, they are on the basis of how the discoveries were made and how the links are done. Right, that's why we have the chapter electrostatics first, then the charges begin their motion. So we have electrostatics and all like this. Now, class, till now, before starting with electromagnetic induction, we studied about magnetism also. We are through with electrostatics also. Electrostatics, magnetostatics, we are through with them. Now in EMI, AC, EM waves, we'll be linking all these. Now we know the concept of magnetism, we know the concept of electrostatics, we just have to link these things. So in the last lesson, not the last to last, that is chapter 4, magnetic effects of electric current, moving charges and magnetism. There we had seen that when you have a current carrying conductor, it produces magnetic field, right? Because we had seen that current carrying conductor, we applied Biot-Savart's law also, right? B is equal to mu naught ideal sine theta divided by 4 pi r square. That gave us the magnitude also of magnetic field. There was a question that arises that if we interchange this, suppose there is a magnetic field present in a coil, and that magnetic field which is present in the conductor, is it able to produce current? Current carrying conductor is able to produce magnetic field. We'll calculate its magnitude. Different devices are there, circle, square, the straight wire. But if we reverse it, if there is a magnetic field in a conductor already, not because of current, because of any other source. So if we reverse it, will we be able to get current or not? This was a major question that arose at a particular time era. So the answer to this was yes, definitely. This was proved. So we'll see how, you will see how current is generated. But before understanding anything, you have to have the basic knowledge of magnetic flux. Electric flux we have studied. Electric flux was what? All these things we'll do in the revision classes as well. But before we start with the revision classes, before we complete with the syllabus, you all also know should link things. Electric flux we've already studied before starting with Gauss theorem. Electric flux was number of field lines crossing area perpendicularly. Here simple, number of magnetic field lines crossing area normally. Formula is also same, where you had electric field, now you will be using the term magnetic field. That's it. Okay? So number of magnetic field lines crossing area normally. Suppose I have this surface with me. There are few lines which are passing. These are magnetic field lines which are passing. And with the surface, no, they are making angle at this surface. They are making angle 90 degree. Right? So I'll just calculate 1, 2, 3. So flux is 3. That's it. But see class, there were 3 lines over here. So 1, 2, 3 I could calculate and I could get magnetic flux. If so many lines are present, magnetic field is not visible, then what will I do? How will I count the magnetic flux? So for that purpose, we obviously require a formula. So no derivation for this. Formula is also very simple. If there is a surface area, an area is present, whose surface area we take it as S. B is the magnetic field line. Now, we always take perpendicular to the surface. Why? Because the definition of magnetic flux says that number of magnetic field lines which are crossing area normally. Find number of magnetic field lines which are crossing area normally. So we have to take, if magnetic field is not passing normally, means not normally here means 90 degree, not normally or abnormally. 90 degree is the term when I refer to normal. So we take the term area vector. We automatically by ourselves draw a perpendicular to the plane surface. Suppose this is a plane surface present. So whether magnetic field is present in any direction, what is our work to do? We'll take a perpendicular to this surface. Anywhere. If the surface is like this, perpendicular drop. Surface is tilted, tilted. Surface is tilted, tilted. But perpendicular to this surface should exist. That's it. All right. Now see, the concept here is that the angle between magnetic field line and the area vector, this term we call this perpendicular, we call as area vector. So angle between magnetic field and the area vector, we take this angle. Always remember, because in some questions you will get the angle between, be careful class with this line. In some questions you will get the angle between magnetic field and the perpendicular. You will get the angle between the magnetic field and the perpendicular. This is also given. So don't consider that, don't calculate it. What you require the angle between magnetic field and area vector, and at any cost you will calculate it. Fine. Now these are the terms which are present. For us, magnetic flux is equal to B dot S, that is B S cos theta. All the terms we have predefined, and SI unit is C. Magnetic field is Tesla. Surface area is meter square, which we can write it as Weber also. Tesla meter square is written as Weber also. Write it down. Let's see some numericals. See, this question says magnetic field of 2 Tesla exists in space. It is inclined at 30 degree with the plane. See, 30 degree with the plane, not with the area vector. That is not with the perpendicular, with the plane. If this is the plane given, magnetic field, this inclination is 30 degree. Do we require this? We require this angle. That is 90 minus 30, which is 60 degrees. So don't use BS cos theta, 30 degree as your theta. Clear, class? Now question is very simple. You have for magnetic flux, you have to apply BS cos theta. So magnetic field is 2, surface area is 10 cos 60 degree half. This is 10 papers. Noted down?
Excuse me, ma'am.
Yes, Vadil.
Ma'am, can you explain the angle that we have to take again in BS cos theta?
See, suppose you have a surface. This is the surface, fine? Plane surface you have. Now, at this surface, this is the area vector which we have to consider. Correct? Perpendicular. Now see, suppose magnetic field which is present is at a certain angle. Suppose magnetic field is inclined like this. So the angle between if you take the angle between magnetic field and the plane, see this angle. This is the angle between plane and magnetic field. We do not require this angle. We require the angle between, this is the perpendicular area vector, this is the magnetic field. We require this angle. Now, what did the question say? Question said that it is inclined at 30 degree. It what? Magnetic field. Magnetic field exists, no? 2 Tesla. So it is inclined at 30 degree with the plane. This angle is given. Normal, that is area vector, is making 90 degree. So how much this will be? 60. Clear? Fadil?
Yes, ma'am. Yes, ma'am.
Let's see the next question also. Written, na? Above question, have you all written?
Yes, ma'am.
This says, okay, the same question in Cartesian form. Magnetic field of 10 I cap plus 3 j cap plus k cap exists in space. Calculate flux through an area of 2 meters square in YZ plane. See, magnetic field, this is given as 10 I cap plus 3 j cap plus k cap. Now, what about the SI unit? See, sorry, not the SI unit, surface area. Surface area is given 2 meters square. But this is the Cartesian form we are writing. So if we are writing Cartesian form, we have to specify I cap, J cap, K cap. So if it is saying YZ plane, class, what is YZ plane? YZ plane is this. This axis is Y and this axis is Z. So YZ. Now, when we are talking about the surface area, whenever we are talking about the surface area, where should the area vector point? Perpendicular. So perpendicular to YZ. Which axis is this pointing to? Perpendicular to YZ. Answer, class. Perpendicular to YZ plane is
X,
Fadil.
X, X, ma'am.
So for x-axis, which unit vector you have?
I cap.
I. So we'll be using the unit vector I. Is it clear to
Yes.
others also? Aliza, clear? Aliza, you're very inactive in the class. Just keep on
Yes, ma'am. Yes, ma'am.
answering. Okay. All right. So we'll be using I cap. So this is I cap. So magnetic flux is B, that is 10 I cap plus 3 J cap plus K cap dot S, that is 2 I cap. Now see, J cap, K cap have no coefficient, that is 0. So 3 into 0, 0, 1 into 0, 0. But here you have the component 2 into 10. This is 20 waves. That's it. Write it down. Let's start with Faraday's laws of EMI. T class, there were certain Faraday's experiments conducted. He observed, he just constructed a circular loop. This was a wire attached to a galvanometer. Galvanometer is used to detect the current. So it was observed that when a bar magnet was brought closer to the circular loop with a certain velocity v, there was a deflection observed in the galvanometer. Fine. Reason behind this is that when the bar magnet was brought closer, magnetic field lines increased, and so the magnetic flux increased, and because of this current increased. So I told you, yes, it was observed that yes, current is produced, which was the main question of that era. This was the reason. Current was detected. As soon as this was brought closer, this started deflecting. So it means there is current produced whenever bar magnet was brought closer. Then what did he do when the bar magnet was taken away with v velocity? So magnetic field line decreased, magnetic flux decreased, current also decreased. Means the deflection, this decreased a bit. Then when magnetic field bar magnet was not moved, nothing happened, no deflection was shown. So this showed that yes, current is present whenever there is motion. That was the first experiment. Second experiment concluded the fact about the current and potential. It means whenever, see, this time what he did, Faraday, instead of moving the bar magnet, he moved this. He moved the coil. The coil is moving this time with v velocity. This is the velocity of the coil. Then also it was noticed that yes, current was induced as well as potential also was induced. And we call this as induced current and this as the induced EMF. Now this was a third circuit. This was a wire connected in which it was wrapped on an iron rod and connected to galvanometer and finally connected to rheostat, key and battery. So here the current was not stable. He shifted the resistance continuously. So basically this was observed in alternating current, and we'll be studying this about alternating current itself. It was observed that a fluctuating current was observed. That is alternating current. Here we will not discuss it. Now conclusion. Faraday's laws of EMF. Faraday basically says the fact that whenever the magnetic flux linked with a circuit changes, induced EMF and induced current is set up. This was concluded correct? Correct or not? That is what we have seen. Mainly the important circuit is the first one. Important experiment is the first one. Second, it says the higher the rate of magnetic flux with the closed circuit, greater is the induced EMF. This means that magnitude of induced EMF is depending upon flux. Whenever magnetic field lines increased, flux increased, so the current also increased and so the EMF also increased. That is what were the conclusions of his experiments. So what he could draw was the fact that, see, first law of Faraday says that this induced EMF is directly proportional to rate of magnetic flux. Right, magnetic flux created per unit time. That is what is meant by magnet rate of change of magnetic flux. So whenever magnetic flux linked with a coil changes, and EMF is induced, which is directly proportional to rate of change of magnetic flux. When I say rate of change means, let's say phi I is the initial magnetic flux, phi F is the final. So when I talk about the change in magnetic flux, that is final minus initial, which is the change in flux. Correct? So basically this rate of, and what is rate? When I say this is change in flux, but what is rate of flux? Rate of change in flux, that is change in flux by change in time. This is what is known as rate, something which is changing with respect to time. So Faraday basically concluded the fact that EMF is directly proportional to rate of change of flux. Fine. So ultimate formula is minus d phi over dt. Now, what is the question about this minus sign? Okay, this is clear. This is clear that this is EMF. This is clear that this is rate of change of flux. What is this negative sign? So we'll have a long discussion on it. This is a law which is known as Lenz's law. See, this is a separate topic we'll be studying. Fine, this is known as Lenz's law. This I'll tell you later. But this is what are the two laws of EMI? What are the two Faraday's laws of EMI? Class, I'll ask you this in the next class also or today also. First law says that whenever flux changes, either it is increased or flux is decreased, there is an induced EMF and induced current. This is the first point. Second point says that when the EMF is produced, its magnitude is directly proportional to rate of change of flux. Are these 2 points clear to all of you or not? Should I repeat any point? Rajita,
Clear.
clear?
Clear,
Yes,
ma'am.
ma'am.
Sidra?
Yes.
Okay. These two then I'll tell later, these formula. Write these experiments quickly. All of you have attempted the Friday's exam.
Yes, ma'am.
Okay.
Yes, ma'am.
Fadil, Eliza have. Others, Deborah, I think you also have attempted, no? Deborah? No. And what about you, Sidra and Amna? Rajita? Attempted the Friday's
No,
test?
ma'am. I'm sorry. No, I didn't.
You didn't. Any reason, Rajita?
No, ma'am. I just biology had a lot of portions, so I kept concentrating on that.
Okay, and what about others? Amna, Deborah, Sidra? Attempted or not? Because I haven't checked your papers. I have not checked your papers. I'll check it. But I just wanted to know who all have attempted. Please keep on attempting these. I hardly gave 3 questions. No? Aliza and Fadil, there were hardly 3 questions.
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
Okay, Deborah has attempted. Amna and Sidra, both of you haven't. Okay. Do take the question paper, at least just see the questions. Yes, class. If you have written till here, now in the next class we'll continue Saturday, Sunday we'll complete EMI. We'll be able to finish it. Small topics are there: Lenz's law and induction. Okay, class. Thank you so much. Let's meet next.
Thank you.
Thank you,
Excuse me,
ma'am. Thank you.
Aha, Fadil, say.
ma'am, can you explain how we got the negative sign again in rate of change of flux?
नहीं नहीं